this is something you should be doing at a later stage, right? Um, so this is teaching students about the concept of computational chemistry, right? Which some people refer to it as molecular modeling, and they both, like, people use this word interchangeably, where it's computational chemistry and materials modeling. I personally usually like to give these two separate domains, where computational chemistry is basically where you are applying the computational aspects as well as some programming components, where you program tools and things that will make other scientists' lives easier. So that for me is the computational chemistry piece. Whereas the molecular modeling is you're just taking tools that are already available to you, and then you're applying these tools to chemistry research. So that for me is the primary difference between the two aspects. But everybody's got their own way of thinking, so I will leave that one up to you. Right, so in computational chemistry, we have various methods. Now, before you can even dwell in the computational chemistry aspects, you have to know what methods are out there and available for you. So there are a few, and these typically are molecular mechanics, Hartree Fock, post-Hartree Fock, semi-empirical, and density functional theory. Then there's hybrid QMMM, and then something called molecular dynamics. So I'm going to touch on each of these sections during this talk today. I'm not going to go into very deep detail of the maths and the physics behind it, but it's just to give you an idea of where one would apply these different methods and to what type of systems you would want to apply these methods. Okay, so molecular mechanics, if we start, right? So this is based on a model of a molecule being a collection of balls and springs. So each atom, sorry guys, can you just give me 1 minute? I'm in a meeting at the moment, so yeah, later. Um, so if you look, you have balls and springs. Each of the atoms is represented by a ball. So here in this case, you'll see the carbon atoms all have these grayish balls, and then the hydrogen atoms have this white ball on the top. But each of them is bonded by a spring, right? So what happens with springs? You can basically, you can expand a spring or you can contract a spring, right? But you can't break a spring, basically. Now, that's one of the crucial things when it comes to these molecular mechanics models is that they're also known as force fields. And everything that's in this force field is a parameter. So if there's not a parameter available for a particular system you're trying to study, molecular mechanics is not going to work. So it's just something that you need to know that if you get an error from any software package because it's complaining it cannot find a certain atom, it's most likely because that atom doesn't exist in the parameter set. So this is something to keep in mind when you run these types of simulations, right? And the molecular mechanics is basically just defined in terms of various different energy terms, right? So when you get a stretching term, this would be used for when you have two molecules that are bound together and they're able to stretch and come back to its normal form. There's bending motion. The bending will happen when you have three atoms that are bonded together. So you have an angle that you can then bend. There's also something called a stretch bend, which while you're bending the one, you might be stretching the bond of another. There's outer plane. So this is basically you have four atoms that are bonded, but three of them are out of the plane of the page, so you can kind of squish them up and down. Then there's a torsion, where four atoms are bonded in a straight line, and then you're allowed to twist them. Then there's van der Waals and electrostatics. So these two, basically this whole section up until the torsions is known as your bonded terms because atoms need to physically be bonded together in order for you to get those terms. Whereas the van der Waals and electrostatics are non-bonded terms. So they don't need to physically be bonded, but as long as they're close enough to one another, they can be experiencing these interactions. Right? So, and you'll see that I make mention of different force fields that are here, but this is just a few. There are various different force fields that currently exist. So depending on the software packages you make use of, you can use many different force fields. So as you can see, there's Amber, there's Gromos, there's Charm, MM2, MM3, UFF, OPLS. So I will show you a little bit later in the presentation about the different software packages that we actually have. And then I will show you exactly where some of these might be applied, in which software packages you can find them. Now, there is no one that's the greatest when it comes to molecular mechanics force fields. It all depends on the system that you're trying to study, right? And this applies to any of the methods that we look at today. That depending on the type of system and what you're looking for, you have to choose the right method for whatever problem you're trying to solve. Right. The next piece is then based on quantum mechanics. So we covered molecular mechanics. We know everything is parameters. And if there's no parameter, unfortunately, you're going to have to find an alternative route to try and solve your problem. So the other methods are based on quantum mechanics. And basically, quantum mechanics, the goal is to solve this equation, right? Which is the Schrodinger equation. The thing is, though, that fine, so these terms are broken up into your Hamiltonian, your wave function, and your energy, right? So the goal is to try and minimize this energy and get it to a form that is considered in equilibrium, for example. And but this equation can only be solved exactly for a single electron system. So the hydrogen atom or the dihydrogen, which is then positively charged. So again, it's only single electron. The moment you extend over more than one electron, you no longer can solve this exactly. What you're going to have to do is you have to approximate. So there's various different types of approximations that people have developed over the years to try and solve the Schrodinger equation. One of which is known as Hartree-Fock, right? So this is a method that was developed many years ago, and this was used for the multi-electron problem. So where you have more than one electron in the system, and in chemistry, we know this is for everything, right? Almost everything we do has more than one atom, there's more than one electron, so we have to try and figure out how exactly we solve this issue. So we can use then this Hartree-Fock method. There are no parameters when it comes to Hartree-Fock, right? So unlike molecular mechanics. And what you're doing is you actually solving each of these different integrals that make up the electrons and their contributions, but you're solving them numerically. So the computer is going to do the work and calculate some number and give you this number at the end. And that number is going to maybe correspond to your energy of your system in its particular state. So they obviously, there has to be a way that the computer needs to know when to stop, right? So this is why they make use of a process called iteration when you work with any of these quantum models. Is that you start off at a certain point where you give it a structure, it then changes the structure up slightly, calculates a new energy, changes up even more, calculates a new energy, and so on. And it keeps going until it gets to a point where it sees that two or three energy terms do not change. So whether they're changing the configuration slightly and you calculate the new energy, there is no change, right? So here is just a small animation of how the process happens. That when you're doing an optimization, you start your structure off at a certain point. It then takes number of iterations till it gets to a point where it's happy with the structure that it has. One thing you'll notice though is this I've used as an example of butane, right? So butane has a CH3 group here. It's got CH2, CH2, CH3. Now you'll see that this CH3 and that CH3, they're quite close to one another. Now, of course, it is a minimum because if we consider the Gaussian anti-effects of the different butanes that when butane changes its dihedral angle, this is the optimum where the CH3s are across from one another. But of course, the other energies are a bit higher. So this is a minimum energy conform. However, it's not the global minimum energy conformation. So this is one of the things that you have to keep in mind when doing quantum mechanics is that if you run a simulation of a particular structure, there's no guarantee you're going to get to the global minimum. There's a good likelihood you're going to end up in the local minimum. And often that might be good enough for you to actually still just compare to experiment and continue with other analysis along the way. But if you're searching for the global minimum, there's a number of extra techniques that you're going to have to apply in order to actually find this global minimum. So it's a lot more work that needs to be done. So for this presentation, I'm not going to go into the detail of that, but just to pinpoint the fact that make sure that you know when you're doing quantum, if you are just taking a structure and you're optimizing it, you're not necessarily in the global minimum landscape. So there's many other things you may need to do to actually get to that point. Right, so after Hartree-Fock came your post-Hartree-Fock methods. So the post-Hartree-Fock, they basically added electron correlation because Hartree-Fock itself does not do electron correlation quite well, right? So by adding in this electron correlation, they make things more accurate by including things like repulsion between electrons and repulsion where with the Hartree-Fock, the repulsion was only averaged out. Now, remember, averaging something sometimes never always the best route to go, right? So here you want to rather get the electron repulsion for every single interaction that's happening between the atoms. And that obviously is more accurate, but it's more time consuming. So these post-Hartree Fock methods, which I've given here, they are extremely computationally intensive. So simulations can take days, if not months, for large systems. So this is a problem that if you're going to run these simulations for very big systems on using these methods, you're going to have problems. Your biggest issue being that you're going to wait. And some of you that might be doing an MSc or PhD, if you've got a substantially large system, if you're willing to wait your entire MSc or PhD just for one simulation to complete, I guarantee you, you're not going to be done with your postgrad studies in that. So the best thing is to make sure that you don't do that, right? So you want to use these methods usually as like a fail-safe later on. Maybe if you already have a structure that's optimized at a lower level, then you can actually then take the energies and then optimize them further, for example. Right? Let's so this is just something to keep in the back of your mind that often people, when you look at research papers on this topic, they typically would make use of these methods for very small systems, or for the larger systems, they do just what's called an energy calculation and correct the energies based on these methods. Right, the next method we have is semi-empirical. So for semi-empirical, it's also based on the Schrodinger equation, but it's a bit faster than your Hartree Fock, actually substantially faster than Hartree Fock. And mainly due to the fact that now you're working with both parameters and quantum mechanics. So each of these quantum mechanical simulations, they typically will take many, many different integrals to solve the problem. So what semi-empirical does is it takes some of those integrals and actually makes them parameters that are basically hard-coded values which people have developed over time for some or other system, and then they plug them in. So those values no longer need to be calculated. They just get pulled from a database and then get run on the simulation. And then other quantum properties can still be calculated as you would with the conventional quantum one. So of course you can imagine it's quite fast. But semi-empirical, the issue is that it has the same drawback as molecular mechanics, in that if you do not have parameters for a particular molecule or atom, your simulation will not work. It will give you an error. So it will just probably crash out and tell you, look, there are no parameters for this atom. So you will then have to go and develop those parameters if you really want to use semi-empirical, or you're going to have to go to quantum mechanics. So the higher level quantum mechanics. Right? So just something to make sure that you remember that there are drawbacks, right, to all of these methods. Some too slow, some might be no parameters. So there's these issues that you have to iron out when you run certain calculations. And so there are various different semi-empirical methods. I only highlighted a few here. These are some of the more popular ones that I use. So there's Austin Model 1, parametric method number 3, parametric method number 6, and parametric method number 7. And often these methods are basically improvements on the previous one. And then there's a relatively newer one, which is called self-consistent charge density functional tight binding. So SCC-DFTB. So this is a method that is currently used quite often by a lot of researchers because it's based primarily on DFT, but there are approximations. So that's why they changed the name to tight binding. So there are still approximations, there are still parameters involved. So you can still end up with the same situation where you will not get answers for systems that are not parameterized. Right, then the most famous method, which I'm sure most, if not all of you have heard about, is density functional theory. So density functional, the primary difference between it and its predecessor, which is Hartree Fock, is that instead of now calculating the wave function like the Hartree Fock does, density functional is based mainly on the densities. So it makes use of the density of the molecules as opposed to using the wave function each time. And by doing this, they actually speed up the calculation. So DFT then allows things to run faster than Hartree Fock does and still give you accurate results. But there are various different DFT methods, and I've only highlighted a few here because if you go look up papers, you will find there's like a cohort of different DFTs everywhere. So you have the generalized gradient approximation methods, the method GGAs, and then the hybrid functions. And there's also something known as the LDAs, which I haven't specified yet. Right. So these are just examples of a few, as I say, some of the more popular ones that a lot of people are using, but there's many others that one can actually use. So many have been developed over the years. So if you want to, you're more than welcome to have a look and you can go and find other methods. And everybody has their own preference. Because there's a lot of people that love to use B3LYP, but in my research group, I'm not really a fan of it. So I typically might use MO62X for organic systems. So everybody has a preference and they all have their ups and downs. And they all can give you results for certain things and maybe not results for others. So it all depends on what you're looking for. Right, then there is the QMMM methods. So this is actually something that a bunch of chemists won the Nobel Prize for in 2013 for the development of this method. And it was Arya Waschel, Michael Levitt, and Martin Karplus that actually won the Nobel Prize in 2013. And Michael Levitt's actually South African, by the way. So uh, what happens with QMMM is that people were looking for ways to speed up calculations without bringing in the full quantum mechanics of the whole system. Because you can imagine now, if you look at this is a protein in the background. If I were to treat this whole thing quantum, I would spend years waiting for that one calculation to finish. But if there's only a piece of this system that I'm interested in finding out what is happening quantum mechanically, then I will treat that piece with quantum mechanics and then treat the rest of it with normal molecular mechanics. So I allow the rest of the system to still just minimize using molecular mechanics. But there could be a reaction maybe taking place inside this active site in this case. Or in the case of heterogeneous catalysis, if I have a catalyst, which is a very big, bulky surface, I need to then make that molecular mechanics. But on the surface, there could be a reaction happening with maybe carbon dioxide that I want to actually simulate. So I'll treat that part quantum mechanically so I can model the reaction while still keeping the rest of the system intact without having to now completely cut it out and just maybe use charges, for example. Right? So this is proving to be very effective for a number of simulations these days. And because of the computational technology we have, they aren't as slow. So there's people developing things all the time that are making these methods a little faster and faster as time goes by. Right. So what does this do? Basically, what do you do is to calculate this QMMM energy, you need the quantum region. You also need the MM region, but then you need to remember there's a boundary in between these two, right? So this boundary you need to then model where you say, okay, how do I model this boundary? So here they use what's called a coupling constant. So this coupling constant is made up of all the electrostatic interactions that take place, the van der Waals and the covalent. So here you usually won't get covalent bonds. I'm not going to go into the detail of how you would break a covalent bond if that were to happen, because there are systems where you have to cut along a covalent bond, and that's a whole nother story of its own. For now, we're going to assume that there's no like physical connection between the QM and the MM region, and that you can just break your QM part and keep your MM separate completely, right? So then this is what one would use. And then there's two primary embedding schemes that they make use of. One is known as mechanical embedding, where this electrostatic term, that term is basically calculated at the MM level. So they use this molecular mechanics level to calculate this um, classical Coulomb term of point charge interactions between the QM and MM regions. So the boundary will basically just represent point charges of the MM atoms. Whereas if you use then the more accurate method, which to me I believe is more accurate, is the electrostatic embedding. Here then you treat that boundary actually at the QM level. So you allow the quantum mechanical level to treat the boundary region. And then that QM energy is calculated in the field of the MM point charges which lie outside the boundary. You get point charges here. And that results in your quantum electron density. So it basically then allows for polarization to take place, right, by the environment. So your van der Waals and your covalent, that can still be calculated at the MM level. But at least the electrostatics need to be done at the QM level. So obviously that's going to make your calculation a little bit longer because you're calculating it at the quantum level. But it's been proven to be a bit more accurate when it comes to simulating some reactions that take place in this QM region. But then the last of these methods is molecular dynamics. So fine, we've got a relatively large system. We now want to say, now, as I've shown you with quantum, what does it do? It takes a structure and it goes to the next closest minimum energy conformation, right? So that's considered optimized. The thing is, it's not taking motion into consideration. Like, how are these atoms moving constantly during the course of time? And we know atoms are never standing still. So quantum mechanics on its own doesn't ever do that. So usually you have to bring in molecular dynamics. So dynamics allows for free motion of all of your atoms in your molecular system during the course of a simulation. Then what you do is you first assign the velocities for all of these atoms, you calculate the forces on all the atoms, then you use Newton's second law. So F equals ma, right? So the forces are then calculated for how all of these atoms are busy moving around. You calculate the velocities for the next step, you use the change of velocity to get the coordinates for the next step, and then you do it again, right? So you keep repeating this process so that every single atom is allowed to move, and then typically you would run it over a certain simulation time frame. So usually, if you're doing it on a bioscale with only molecular mechanics, you would work in a nanosecond time scale. If you want to do quantum dynamics, you're typically going in the femtosecond or picosecond range because they take much longer because everything is now being done quantum. So if you do it with QMMM, you can also possibly get to the nanosecond range, depending on how fast the code actually can run. Right, the one final thing that I didn't touch on in my methods is machine learning. This is the big thing. Everybody wants to do it. Everybody believes that the data needs to go through some machine learning process in order for it to be more accurate or for predictions to be made. Yes, that's all well and good, but it's important to remember that the machines can only learn from what we give, right? So if there's issues in your data set or there's points that you are uncertain of that whether they fit your data set or not, feeding that into a machine learning algorithm may result in the wrong answer coming out at the end. So you need to be very careful when using these algorithms. That for one, you need a lot of data. You cannot take like 10 points and expect to do a machine learning sort of algorithm with 10 points and then say, okay, I can make predictions for, say, the next 2 points. That's not going to work. So what you need is you need a relatively large data set so that the algorithm can actually learn from all of the data and sort of incorporate errors here and there where it needs to. And from there, then make predictions. So when I say relatively large in computational chemistry, we have lots and lots of data. So sometimes, even if you're looking at like million or so data points, you could probably try and use a machine learning algorithm for that. Some people do it with hundreds of points. That also can work. It's just that you don't want to train a model for too long because you often run in a situation where you can overfit your data. And overfitting then means, yes, you've now learned and you've trained this model to learn this thing. But when you overfit, it will only work for your data. The moment you come and bring data from the outside that doesn't necessarily fit your data, it's going to say, oh no, it's wrong. But in actual fact, it could have been correct. So you have to be very careful that you don't overfit the information that you're actually feeding into these algorithms as well. So typically, we in the field of computational chemistry, we've been using these for quite some time now. So it's not just a new thing because of AI and machine learning. Uh, Typically, one would have been using it for things like quantitative structure property relationships or quantitative structure activity relationships, which a lot of you may know as QSA. So these QSA models were things that people were using sort of machine learning algorithms to train from and then make predictions thereafter. So yes, on the quantum level and in terms of materials, I mean, it's also getting very big these days because there's a lot of data out there when it comes to either materials or biomodeling. So it's all a matter of taking the data and feeding it into this algorithm and then trying to train it for the correct thing. Because if you train it for something wrong, it's going to give you an answer. It's just not going to give you the right answer. So this is the whole thing that computational chemistry is one of those disciplines where if you put rubbish in, you're going to get rubbish out. So there's no difference when it comes to these machine learning algorithms. So here in this case, you'll see people use electronic structure calculations where they'll get certain properties, feed it into the algorithm, and then it trains itself. From there, they have usually what's called a test set where they can make predictions, and then those predictions they can then feed into more electronic structure calculations to see if the data fits the way that the model predicts it should. Right, so now we've done the methods. Now, what about the software? So, yes, there's lots and lots of different software packages out there. And I've not even listed all of them here. I've only listed a few, just because these are the ones that are primarily used by researchers that I know of in South Africa that make use of computational chemistry or materials modeling. So the first one is Amber. As I told you, it's also a force field, but it's a software package as well. So this is able to do molecular dynamics on biomolecules. And very recently, this package actually became open source. Uh, for a very long time, they were licensed, so you had to pay a certain license fee in order to use it. But now it is open source to all academics. So that's a plus, right? Then there's Autodock, which is used for molecular docking. So this is if you're in the biofield and you want to dock sort of drugs into active sites, you would then consider using Autodock. Avogadro is just a visualizer. So this is just used to visualize your different molecules that you're building or molecules you might have crystal structures for, you can actually visualize in this. And this is also open source. Burai is also another open source package, which is used for primarily materials. And it is an interface for another package which I'll mention later known as Quantum Espresso. So that allows you to then set up simulations for that software package. Charm is an MD package. Again, also they very recently became open source. CP2K also MD for more for materials than for bio. DR Poly, same MD for materials. Gauss View, this is licensed. So a lot of you may know Gaussian, which is also a quantum package. And basically Gauss View is just the visualizer for Gaussian. And it is something you have to pay for. However, I would suggest to you, if you plan to use Gaussian, there is nothing wrong with using Avogadro to set up and run calculations with Gaussian and also visualize the output that comes out from Gaussian with Avogadro. So there is an open source option, right? I'm always for the open source because we shouldn't need to be paying exorbitant prices for software packages. So just so you know, you can use this to set up calculations for Gaussian and vice versa, right? Then there's Gromax, also open source. That's also biomodeling, LAMPS, MD, materials. Material Studio, very expensive license package, but that can be used for both quantum mechanics and dynamics. And it's used, as the word would suggest, for materials modeling. So it allows you to set up your systems and run simulations on materials. Right? But this is very, very expensive. At the moment, most researchers in South Africa don't have a license to use this. So desktop machines. They look very different. So they actually are things that look like this. Now, all of these lots of cables you see running here, that's your network cables. And basically, each one of these small strips that's on this, that's a node, right? So that basically is what has all the compute resources in it. So if you compare it, a normal everyday computer will have maybe 8 to 12 cores, maybe. So if you compare a computer like this to one of these nodes, right? So just one single node, that can have from 24 up to a give you faster simulation. That's what we would think anyways, right? So they also need to be able to speak to each other, because what if you have a calculation that's running across a few of these nodes? So if the communication between them is slow, then the calculation is going to slow down. So usually these connections are extremely fast. I think with the current times, we're looking at network connections of 200 gigs per second that these things can speak to each other. So if you're downloading movies, it's like not even clicking your finger and the movie's down, right? So basically, that's the speeds that these things talk to each other. So that when your calculations are running, the bottleneck is not when they speak to one another. Right, so we make use of the Center for High Performance Computing here in South Africa. And you guys, as Ghana, also actually have access to the Center for High Performance Computing because you all are one of the Square Kilometer partners. And we will check when I'm done with this presentation because Dr. Kume and them should have some hardware that the CHPC gave them a while back for them to actually set up their own small local HPC so that people from your country can run in their own with their own resources before moving over to CHPC to run stuff. Right. So what does the CHPC have? This is very, very old technology right now, and they're in the process of trying to upgrade it. I'm just waiting to find out when exactly that's going to happen. But when it was first um, obtained, then we had 1,368 nodes, right? Each having 64 or 128 gigs of memory per node. And they also had 24 cores on each node. So you can see memory is not a problem, CPUs are not a problem. So if your calculation is struggling on your own local machine because it's running out of memory, if you have 16 gigs, for example, then the place to take it to is the CHPC because it will probably run there without any issues. Right, and then this is just some extra stats for you guys, but with the current machine that they have, you see they're only communicating at 56 gigs per second, whereas as I said, the new technology is 200 gigs per second that the communication is supposed to have. Right, but now these are normal CPUs, right? So they just central processing units. They like what you get in your desktop or your laptop computers. What is now becoming a big thing is the graphical processing units. So these cards were typically only used for gamers. I myself would know. So over the years, they've been evolving, and the gaming industry has been like making millions off of this stuff. So what NVIDIA decided to do is they decided, okay, fine, since the gaming industry is now all sorted, let's move over to data and big data. And so they started developing cards like this, not for gaming only, but also to process data. And basically, the CHPC's got a couple of them. They've got like 30 of these, which are slightly older cards. They call V100s. And essentially, what these things can do is they can process the information much, much quicker than your normal CPUs can, provided that your program actually can run on them. So if the software is not able to run on a GPU, it's pointless trying to submit a job to the GPU because it's never going to run there. So you have to make sure your software package actually can run on here. Most, wouldn't say all AMD codes, but majority of the molecular dynamics codes have been ported over to these graphics cards to make them substantially faster. And there are a few quantum codes that people are working on, but it is proving to be a bit of a problem to get the quantum stuff actually running on these GPUs. So for now, CPU is the better option for quantum mechanics. Right, so how does it work? So you are sitting in front of your laptop here. You then, via some connection, so unfortunately, there is no click and drag and drop interface when it comes to using HPC. You have to at least know a little bit of doing stuff on the terminal, but it's things that you can learn, right? So it's not too hectic. You just have to find a appropriate terminal. So if you're a Windows user, there's something called Mobile Xterm, which I usually refer people to. This will allow you to bring up a terminal or black screen that you will then use to do what's called SSH. So establish a secure shell connection between yourself and the login node that's at the CHPC in this case. Right. So once you actually log in there, you're no longer here. So in that black screen, you're actually sitting on the CHPC machine. And from this machine, you then go through a scheduler. So scheduler is just like if you were to think you were at a shopping center, you're busy doing some shopping, and you now basically buy some goods. You obviously have to queue, right? You don't just jump the line. If there's a line, you have to queue. So this is essentially that queue. It helps with distributing the jobs to the actual cluster itself. So it then determines, okay, you have a job that wants two nodes, somebody wants a job that wants one node. I'm going to let that guy go in first because his job will run faster, or I'm going to let him go first because there's only one node available right now. And then you'll have to wait. So that's when you queue, right? So because you're sharing this resource with lots of researchers from both Ghana and other African partners, as well as all the South African researchers, you often do end up with situations where you sit in a queue for quite a while before your job can start running. So again, you have to just see now, okay, would it be better if I just run it on my local machine? Will it run faster? Or while I'm waiting, maybe I can just leave it to run on my local machine and see what happens. That is also an option. So there's a lot of things that one needs to take into consideration. Just like if you were to work in the lab and you need the chemicals, these are our issues as computational chemists. Right now, I mentioned to you guys that we would assume if you run a calculation on more CPU cores, it would get faster, right? So here's just a typical example. So we're going to focus more on this opt-in freak part. So this was for a reaction where we had reactant in the blue, product in red, and transition state in green. So just looking at the time it takes, right? So these are times in seconds. So let's consider the blue line. If you look here on one node, which is 24 cores, it runs for 6,350 seconds. If I move it to two nodes, it goes to 4,236. And then it gets a little bit faster, a little bit faster, a little bit faster, right? That's for this example. But in some of the other cases, you see it's not substantial, even here. I mean, it's seconds that it's faster. Is it really worth it? Now, if I were to ask for, say, five nodes, which is 120 cores, there run a good likelihood that I'm going to sit in a queue for a very long time before those five nodes become available. Where in actual fact, if I ran it on one, by the time this thing queued and actually started running, that one might have been finished. So that's what I say. These are things you must keep in mind when you run these simulations. That to try and beat the queuing system, there's tricks. You don't always need to use all of the nodes. And often there are many applications that when you go past three nodes, it actually gets slower, doesn't get faster. So things to make sure that you consider when you're running these types of calculations. But this is just to show you in terms of the actual graphics cards and their performance. So at the CHPC, you have a 12-hour wall time limit to run on the GPU. The same with CPUs. There's actually a wall time. So you can't just run indefinitely and let your calculation go. There's a point where the scheduler will stop your job because you ran out of wall time. So you need to have points where you can restart from. So when it comes to dynamic simulations, what we did was we tested for 24 hours how much can I get, how many nanoseconds can I get in a day. So that's the blue lines. Now, obviously, I have to halve that because I know on the CHPC I only have 12 hours. So if I were to run, say, this very first simulation here, in 12 hours, I can get 57 nanoseconds. So if I were to actually submit a job for 100 nanoseconds, it's never going to get there. And I'm not even going to have a part where I can restart from. So you have to break up your simulation into portions so that you actually have a point where you can restart the simulation from. So in this case, I would say I would go with 50 nanoseconds. I'd run the simulation for 50 and then run the next 50 and the next 50 and so on. And then put all of them together at the end. And the same here. If I had this, I would run this for 20 nanoseconds and break it into blocks. 20, 20, 20, 20 till I get my full 100 and combine them at the end. Because if I had to run 100 here, again, it will run for the 12 hours. I'll get out an output, but I just can't restart that output. So it kind of defeats the purpose, right? So you have to have a point where the job can stop safely so that it can continue with the next portion. Right, and then this is just some benchmarking showing you the GPU performance when it comes to machine learning applications. So if you look here in the blue, is a CPU, which is a Core i7. And the green is actually not even a data science graphics card. This is actually a graphics card which you can use for gaming. And if you look at the performance here, I've got one CPU. That's the chunk that it takes up, right? It's like one time speed up. But on the graphics card, it goes from 20 to 25 to almost 45 times faster for the different parts of the algorithm that are currently running. So can you see? You can sit there for 45 days, or you can sit there for a day and get the same answer, right? So this is where the whole performance thing comes in. And this is where the innovation when it comes to actual graphics cards has basically shot the whole discipline. So we've now been able to run much bigger models because of the fact that these cards can run things much faster. And of course, we now have the new quantum era, right? So remember, this is the year of quantum. So there's a lot on the whole quantum computing, and computers can actually make the stuff, even these cards, look slow. So we all waiting to see when actual applications can be run on these quantum computers and when we can get access to these things. But at the moment, it's looking like it's a very pricey thing. Right. And then just to end off, so to apply the computational chemistry effectively, one needs to know the problem you're planning to address, the methods, right, which I've explained to you guys, the MM, the QM, your QMMM or your MD, the software that you want to use, and then you need to make sure that you effectively and efficiently using the software on the hardware that's being made available to you. Because yes, it's okay if you're running it on your desktop and you must use your desktop, but if you're running it on a public resource where everybody and all other researchers are making use of it, it's a problem if you are using too many resources but your application is using less. Those extra resources that you're not using, somebody else could have been using, right? So one has to be considerate and also make sure you monitor your jobs and check and make sure that everything is running efficiently. Right. And then as a final thing, I would just like to thank the Department of Chemical Sciences at UJ, my research group, the E equals C squared M squared group, and then my mentor, Professor Penny Govender, the CHPC, where we basically saw some of these benchmarks that I did. And then finally, I would like to thank the CSR Ghana for inviting me to give this talk to you guys. And thank you, Dr. Kumi, for the invite.
You're welcome, Prof. You're welcome, Prof. Okay, Mr. Alex, can I take over now? Mr. Alex. Okay, thank you very much, Prof. For Alex, can I take over now? Okay, we'll open the floor for questions and then answers. And I think it has been a long talk of chemistry, Prof. A lot of people say that, hey, you're about to teach us only chemistry. But that is
But
very
because
good.
it's computational chemistry, it's not computational something else.
It's a lot of chemistry. That's it. That is very good. And it's a very nice presentation. And I hope that we can even do another talk where we'll look at also the general aspect of research trends in the future. So I would like to open the floor for questions so that Prof can assist us. Thank you very much. Please, if you want to ask a question, you can raise up your hand.
Okay, thanks for your talk. And maybe make that list or table of all the software available. Oh yes, I can. Um, Dr. Kume, I can share my slides with you. I think at the end of this.
That's perfect. That's perfect. Please can ask a question now. If you have a question, you're allowed to talk, please.
Yeah, hello.
Yep.
Yeah, great. Good morning, and thank you for the insightful presentation. Just to touch a bit on the molecular dynamic part of the presentation. You listed a number of, I think, hardwares and also the time it will take to generate an MDS data. If you could shed some light on how this was benchmarked to give me a clearer idea as to how the hardwares performed separately. And also, my second question is more of a request that perhaps going forward you could pick one of the MDS softwares and probably shed some good light on it. I am quite familiar with Gromax, so perhaps maybe you pick one of them. Especially, I'm more interested in the part where you could run the MDS in bits. Maybe you can run 20 nanoseconds and 20 and then piece them together. Yeah, so those are my questions. Thank you.
Okay, thank you very much, Edward. So the even if you're using something like Gromax, the same thing applies. You can basically break your simulation up into blocks, right? Because remember, in your Gromax input file, you specify how many nanoseconds you actually want to achieve. So that's the part where you would actually then reduce your time step, or actually keep the time step the same, but then it's the total simulation length that you're going to just make less. So instead of saying 100 nanoseconds, if you work it out, you drop it down to 20. And then you use exactly the same input for the next iteration. But the only thing you do with Gromax is you tell it to restart from the previous one. So that way it'll start from, say, 21 upwards to get to wherever it needs to be. And then the piecing part, there's actually scripts available for whether using Gromax, Ember, doesn't matter. There's actually scripts that will allow you to then converge all of them into one big trajectory to go from 0 to 100 if that's what you desire. And then in terms of the technology and the benchmarking, the way you do that is you take your simulation that you currently have, which you would submit to, say, the CHPC. And if you're submitting the job, you're submitting a 100 nanosecond job, for example. The first thing you do is drop that 100 to 1. Just make it 1 nanosecond. And let that simulation run and finish. At the end of that 1 nanosecond, it will tell you how many nanoseconds it will predict to give you in a day. So that's how I got those numbers that I showed in that slide. That I just ran it for a very short period, and then it makes a prediction of how much it can give you within a day. And then that can give you an estimate of how long you need to run your different blocks for.
Okay, thank you. Yeah. Dr. Kumi, can I do a follow-up?
All right, all right. Why if they
Okay.
Gideon, also.
Okay. So, would you request or come, let me say, which of these MDS tools would you suggest that a beginner should use? Because I've been trying to set up Amber for quite some time now, and the setup is quite difficult, whilst Gromax is much easier to establish. Even NAMD is much easier to establish. So from your point of experience, which of these software do you think is more user-friendly?
Okay, so to be honest with you, in my group, I use everything. So I can use Ember, Gromax, everything. But I would suggest, in terms of ease, yes, Gromax would be your best option because you can also do QMMMD with Gromax. That is currently what I'm pushing a lot for now is more on the QMMM side of things, not just complete everything. So what you're doing now is fine. Gromax is good and it does do more or less the same job that something like Ember would, or even Desmond for that matter. Desmond is also an issue because fine, that's a license package because it comes with Schrodinger, right? So there you don't need to worry about compiling the code. You just have to be able to run it. But there's license issues involved with Desmond. So I would suggest steer clear from the Desmond and rather stay with Gromax. That would be better.
Okay, yeah, thank you. And it looks like even the new Desmonds, they only run on GPU, on Linux. Yeah, so yeah.
Well, that part there has been there for quite a while actually. So yeah, it was a way
Okay.
for Schrodinger to ensure that people can only run the MD on the HPC and they can't run it anywhere
HPC.
else.
Yeah. Because I somewhere, I think the Desmond 18 was able to run on CPU.
Yes.
After that, the rest were all on GPU.
Yeah. So Schrodinger, because they bought the rights to Desmond, you see, so they're
Desmond,
making sure
yeah.
that you have to run on HPC. So
Okay, thank you.
Gideon, Mr. Gideon, or Dr. Gideon.
Okay, thank you. So my questions are in two. So the first one is that between QMM and MD, which one is more computationally expensive to run? And then the second question is, I usually use GROMAC. So post MD, sometimes I run MMPBSA, sometimes MMGBSA, or just PBSA, GBSA. Which one would you suggest is better?
Okay, so one thing I touched on was QMMM. I didn't add in the fact that you can actually do QMMMD, right? So the conventional QMMM, you can do it something like Gaussian even, where you can do onion, where you basically have the different regions. Then it's just a static picture of what you're looking at. But you can also do QMMMD. Obviously, that is slower than normal MD because normal MD works with just straight up MN. So it's only molecular mechanics. The reason for QMMM is there has to be a valid reason why you want to use it. That if you're doing MM, it's great if you're just looking at the binding of maybe a ligand into the active site of something, and you want to see whether it comes out of the active site or it stays bound. So there you can stay with straight up MM. The when it comes to QMMM though, what if you have a ligand that possesses the ability to bind to the active site by covalently bind? Then you cannot simulate that interaction at all because covalent bonding implies breaking and making a bond. MM cannot do that. So you have to then have that region QM so that you can then simulate the reaction that takes place inside the active site. It's more plausible to do QMM when it comes to enzymes because we know enzymes are catalysts. They usually are speeding up a reaction. So typically then that QM region would then be used to simulate the reaction that's taking place inside the enzyme. So yes, in those cases, you can't get away with just straight up MM, they won't work. So you have to do the QMMM. And in cases where you work with metals, I mean, there's some also metalloproteins, right? So if there's a metal there, your MM parameters, even if you get parameters for the metal, they may not be efficient enough to actually model that metal properly. So you may have to go to the QMMM. So yes, QMMMD is slower, but it's all dependent on what you're looking for. And it's not very prominent in a lot of researchers' things right now, but it depends on what you want to find. So I see it becoming bigger, and I foresee it should get a lot of researchers getting involved in it soon. And there are people that are actually working on trying to speed it up. Because currently, I think most of them work only on CPU. So even in GROMAX, remember your QM region for something like GROMAX or AMBER, it's not DFT. So usually they use semi-empirical. So they're either using AM1, PM3, PM6, and nowadays SEC DFTD to model the QM region. If you want to go the DFT level, you obviously need it to be a bit quicker, although it's going to take quite long to simulate. So
Okay,
yeah.
thank you very much.
Uh,
Any further questions?
Oh, Dr. Kume, there's suggestion here in the chat that if the talk was recorded, that you please share it so we can upload it for Saki members as well.
All right. It was recorded, so we'll share with Bemet. Thank you so much. Mr. Alex will do that for us. Alex Gazy.
Okay, so those of you asking for the list, if the talk is shared, then we will also then share the video, so you can obviously find the list on the video.
All right. I think we don't have any further questions, and the presentation was so good. And we would like to thank Prof. Govender for your time. We are looking forward to a collaboration in the nearest future, where we will also be taking through Python and the coding. I think we need more of the codings, and that's the idea behind the whole invitation as well, so that the members will have contact with you. In fact, I have been with Prof. Govender for some time, and he's a very good computational chemist, and he has a lot from drugs discovery and all manner of things. So if you are interested to work with him, this is an opportunity for us to collaborate with him. So, Prof, we'll be looking forward to further collaboration. based on this webinar, if there's possibility for us to do actual coding, what we do, annual coding programs that we do with the what they call it, I've forgotten the name. So that the members will have access to the basic codings, then we can now go into the trends in current research. So on behalf of the CSR Research Staff Association of Ghana, the Southeast Zone, we would like to say a big thank you for this time that you made with us. And also to thank all of you who made time to join us. And we can assure you that there's more to come. So be on the guide. Thank you so much. Mr. Alex, do you have anything to say? Or Betty, our National Secretary? Dr. Betty? Okay.
Yes, Dr. Kumi.
Do you have anything to say?
No, it's been an insightful meeting. So I just want to say thank you again to Prof for such a good presentation. Thank you.
Thank you. Thank you so much. So, Prof, we are done.
All right, thank you very much, Michael. Please make sure you share the recording with me, then I can also then distribute it to others.
We'll do that.
And I'll be more than happy to do the coding thing with you guys. So you will just let me know when.
Perfect. Perfect. So grateful. Okay, Alex, over to you. Thank you. Okay, bye-bye.
All right.